How's it going, folks? We're going to be starting chapter 10 today. We're going to try to make the best of this situation. Thank you for all your hard work with chapter 9. Really astonished at the quality of those tests coming in, so really good job, guys. We just need to make the best of this situation. Could be worse. At least we get to spend some time with our family and loved ones. All right, hope you all are doing well at home and you're all safe. We're going to get started with chapter 10. We're going to look at this problem right here, which is a little bit different than anything we've seen so far. So we've been doing inferential statistics, basically looking at a sample and seeing if we can understand the population just based on this sample. Chapter 10 is really similar to that, but instead of looking at a single sample and trying to figure out what the parameter might be in a single population, we're actually going to use these inference methods to compare two populations. So this is a really useful tool to have, and it's a really, really similar process. It just gets a little more complicated when dealing with two samples. So we're going to take a look at this question right here. In this video, we're going to be estimating the true parameter using a confidence interval. And in the next video, we're going to be doing the exact same question, but using a significance test to answer the question. Okay, so here's the situation. We've got a sample of voters, so we're doing a race for new governor. In the first sample we send out, we interview 415 potential voters, and we get the data back, and we find out 223 out of the 415 said that they favor the new candidate over the incumbent. The incumbent is the person who's already there, already has that position. However, this new candidate makes some unfortunate remarks during the campaign, and so subsequently we take a new sample and we see in this new sample of 630 voters, only 317 favor the new candidate. So our question here is, based on what we're seeing with these numbers, has support decreased for this new candidate? So just to kind of get a better idea of these numbers, we can throw these proportions into our calculator and understand them as percentages. So in the first sample, about 54% of potential voters favored this new candidate. But in the second survey, that number has dropped down to close to 50%. So the question here is, does this pretty small drop, about 3.5%, is that a drop that is due to random sampling variability that we're always going to see? We wouldn't expect the two numbers to be perfectly the same, even if nothing changed. So is that 3.5% drop, is that due to random chance, or is this statistically significant, meaning we should worry that our new candidate no longer has a chance to win? Well, they're still slightly over 50%. But we're worried that they might have lost some favor. Okay, so what we're going to do is we're going to calculate a confidence interval. So we're going to figure out what is our statistic based on these samples. And based on that, and based on the mathematics we've learned and how sampling variability works, we can calculate all of the plausible values for the true decline in voter support. Okay. So to do a confidence interval, like all of our inference methods, we want to follow our 4-step process: state, plan, do, conclude. So we're going to start by stating what we're going to do. So we want to estimate the difference in proportions, so the difference in these two numbers. We're looking for the true proportion, not just this sample. So we're estimating the difference in proportion of voters that favored the candidate with 95% confidence. And by difference in proportion, I mean the difference between P1, the proportion of voters who favored the candidate during the first survey, and P2, the proportion of favors who favored them in the second sample. Neither one of these is our parameter of interest, though. What we're really concerned with is the difference in these two values. So we're going to come up with one last parameter here, PD. Okay, this means proportion of the difference. Sometimes you'll see it as PDIF, but this is sort of standard notation. We'll do this again in 10.2 with mu of the difference. But anyway, the PD, the difference in proportion, is going to be equal to the first proportion minus the second. Okay, so we've stated what we're going to do. Next is the planning step. So in the planning step, we want to name our inference method and check conditions. This will look pretty similar to what we've done in the past. Okay, so we're going to construct a 2-sample Z interval. Zoom in just a little bit here, make sure you can see that. Okay, we're going to be doing a 2-sample Z interval. Again, you always want to name your inference method directly. And we're allowed to do that as long as 3 conditions are met. Remind yourself what those 3 conditions are. You should know it from a single sample confidence interval. It's just going to look slightly different. Okay, condition number 1, we need random samples. So the prompt tells us a random sample here, random sample here. So both samples are random. So we're good on randomness. The next thing we want to check is independence. Ideally, we're working with independent samples. We don't truly have independence here. We're not sampling with replacement, but that's okay as long as our sample is less than 10% of the population. So we can go ahead and assume that 415 potential voters is less than 10% of all potential voters in this state. Same deal with 630. So I'm just going to go ahead and say both samples are less than 10% of all voters in the population. Thus, we can assume independence. So we don't really have independence, but we can go ahead and do the calculations as if we did. Notice that I am checking both samples, and that's the only difference from what we've done in the past. The last thing we need to check is the large counts condition so that we know that our sample distribution is normal, or at least close to it. So the large counts check is when we do NP is greater than 10 and N times 1 minus P is greater than 10. Same deal that we saw in the last confidence intervals, but this time we need to check both for P1 and P2. So notice I'm using P hat, our sample proportions, these proportions given here. So it might be very obvious to you that about 50% of 630 is a number bigger than 10, but they do like to see this shown mathematically. So we're going to take a moment to just throw it on the page. So 415 times about 54% is about this number, which is clearly bigger than 10. We want to check all 4 of those. So same process that we're used to from our old confidence intervals, but just doing this for both samples. So we've stated what we're going to do, and we've made a plan and checked our 3 conditions. So now we can actually go ahead and do the math. Okay, so our do step, we want to actually find our proportions. I did this in the calculator, but we want to get it on the page as well. So I've got my 2 sample proportions, and I want to find PD. Remember, this represents the difference in proportions, hence the D, which is about 3.5%. So I just did this number minus that number, got this number. So this is our sample statistic. We're basically taking our 2 samples, combining them into 1 statistic so that we can find all the plausible values of PD. So really this is P hat D. I should have done a hat there. That is incorrect. Add a hat. Okay, so this is our sample PD, not the real PD. So I need a hat there. Oops. All right. So if I look at my formula chart, then I'm going to find a formula for the confidence interval. This formula chart is on your Google Classroom now, so you can get to that whenever you need it. The confidence interval formula is really vague. It's some statistic plus or minus some critical value times the standard error of that statistic. It doesn't give us a ton of information. We got to really fill in the gaps with all of our knowledge. But we should have that knowledge. The statistic we're using is P hat D, which is about 3.5%. So that's our statistic. A critical value is a z-score. So we said already that we're doing a 2-sample z interval. So we need to figure out what is the z-score for 95% confidence. If we think about our standard normal curve, when we have the middle 95% of the data, so we want the middle 95, then we need to go out about 1.96 standard deviations. So this one you might have memorized because this is the one we use most often. You could also use the empirical rule. We know 95% of the data in a normal distribution is about 2 standard deviations away. The number 2 works, it's close enough. You can use table A, or you can use a calculator. I like using a calculator for this. So just as a review, we would do inverse norm because we know the area we want. We're pretending we don't know what this number is yet. And the area you're going to put in is 0.975. Remember, when you're using table A or you're using inverse norm, we're looking for the area to the left tail from this value. So the middle 95% plus that little tail, which is another 2.5%. That's where I got that number. And we should get 1.96 or very close to it. Okay, so statistic we got from our samples. The critical value we got from our confidence level. A z-score for 95% would give us 1.96. And lastly, we need the standard error of the statistic. So if we go back to our formula chart, we'll see for 2 populations, the standard error of a sample statistic is this bad boy. So this is a really nasty looking formula. We can apply it pretty easily. We're just plugging in the numbers. But this is the point where we start to ask ourselves, is it worth it to do this confidence interval by hand? And the answer is not really. The calculator can do it for you as long as you understand where these numbers are coming from. You can see the relationship between a 2 sample standard error and a 1 sample standard error, basically doing a little Pythagorean sum of those. As long as you understand what's going on, there's no penalty for using the calculator to do the do step. As long as you are showing off that you understand what's going on well enough that it's okay that you didn't write out and calculate this formula by hand. So I'll show you how to do that in the calculator in just a second. But first, let's take a look at our answer. So the confidence interval goes from negative 0.0277 to 0.096. I want you to pause the video and I want you to think about what this means and what our answer to the actual question is based on this confidence interval. So take a second to pause the video and think about that. Right now we're going to do the same thing in the calculator just to remind ourselves how to do something like that. Okay, so we go to stat tests, this menu that we've used quite a few times. So stat over to tests, and we're doing a 2 proportion z interval. We got 2 proportions we're working with, and z is our critical score, or critical value. Okay, so when you get to this menu, it's gonna have you put in sort of the raw stats. 223 successes out of 415 in the first sample. In the second sample, we had 317 successes out of 630, and we're doing a confidence level of 0.95. If we calculate our calculator is going to give us the exact same answer as we got by doing this by hand. You might see slightly different answers based on how you did it, just due to rounding, but at any rate, we get the same conclusion. Okay, so what does this mean? Hopefully you have already kind of paused and thought about what your answer is going to be. So remember, a confidence interval gives you all the possible values, all the plausible values, not possible, all the plausible values for this true proportion difference. So in our sample, we got a difference of about 3.5%, but based on the way sampling variability works, and based on our sample sizes, the true difference between these 2 samples is anywhere between negative about 3% and 10%. So it's possible that voters actually favor the candidate 2.7% more than they used to. It's plausible that voters actually have lost favor quite a bit, up to nearly 10%. So remember, these are all the plausible values of our parameter of interest, the difference in proportions. So let's write our conclusions based on that. So our conclusion usually looks something like this. We're 95% confident that the true change in proportion, PD, is captured by the interval negative 0.0277 to 0.096. Because 0 is in this interval, right? It goes from negative to positive. Because 0 is in this interval, our findings do not support the conclusion that voter support has decreased. Based on what we see here, it's plausible that voter support has not changed at all. Right? Based on these samples, it's possible that the amount of voters that favor our new candidate is exactly the same as it used to be. These numbers are too close for us to make any confident conclusion that anything has changed. It's possible that they're only slightly different. Remember, it's only a 3.5% difference. They're only slightly different due to random chance. So based on this data, we cannot draw any big conclusions here. It's possible that voter support has not decreased. Okay, next time we're going to be looking at this exact same problem, but doing a significance test to basically do the same, draw the same conclusion. Thanks, guys.